is a proprietary software. You have to buy it. It's not free. So you have to pay a whole lot of price to buy it. And our institute has Matlab. So if you can go and use Matlab. Now most of you are on at your homes on our off-campus locations. So you may or may not have access to Matlab. I don't know. But one thing you could surely do is you can get access to Octave. That's why I am going to focus on Octave. But your syntaxes, what you write in a Matlab code is exactly the same as Octave code. So Octave is a free, open source, free software. So you could do a whole lot of things in there for free, completely free, no price. But of course, Octave's capabilities are limited, not as extensive as Matlab. But for us, we don't need all those extensive fancy capabilities. So we are fine with Octave. Okay, so what I'm going to do is I'm going to show you two ways to access Octave. As I said, if you already have Matlab, you have already access to Matlab, fine, great. If you don't for some reason, then you could use Octave as well. So one way to use Octave is to just go to octave.com and then download it from there. So Octave, if you search Google Octave, so GNU Octave, and then from there you could go ahead and there's this download option there. So you could go ahead and download Octave, or another way, if you don't want to download, if you don't have enough, let's say, data to download this thing, and you still want to use Octave, you don't have any online access to Matlab, then what you could do is you could go to Octave Online. So there is this thing called Octave Online. I already have it here. So octaveonline.net. So you could go to octaveonline.net. Then something like this will come up. The web page you see here. This is actually a Octave interface, but it's online. You don't have to install anything. It's all there online. You can go to this website octaveonline.net, and then you'll have access to Octave. Okay, so now what you need to do after you get here is to sign in. So I'm already signed in, so I'll sign out. So once you open this thing, there might be some prompts coming up, like remove all these things, dismiss everything. Finally, on top right, you will see this menu. So menu, you can go and sign in. So you can sign in with Google. So basically, I signed in with my Gmail ID. So when you sign in, you have to enter your Gmail ID and password. So that's straightforward. Okay. So that's Octave Online. Or else you could go ahead and install Octave. So if you install Octave, you will have a software which, if you open, will look something like this. This is approximately this. It might look a little different on your system, but this is what it will look like. Okay, so now what does Octave or Matlab do? These things, I mean, I'm going to talk more about in terms of Matlab, because Matlab is what our final objective is. But these things, as I said, can be done in both Matlab and Octave. And I'm using Octave just so that if you don't have access to Matlab, you know that there is another thing called Octave where you can do everything that we desire to do right now. Okay, so that's the point. So I hope everyone can, I would suggest that everyone go to their website once and see whether you are able to open. But before that, I will just show you a couple of things, how to do these, what these things actually do. So the first thing is, these are actually simulation tools or computational tools. So at the very basic, Matlab is nothing but a like a calculator. So you can use it as a calculator. Suppose I want to find out the value of a plus b, where a is 1 and b is 2. Okay, so I know that a plus b is 3. I want to do it using Matlab. How am I going to do that? The most basic way to do that is to go to this command window. There is a thing that will be called command window. I just put 1 plus 2, press enter, and I see the answer is 3. Okay, so this is, so syntax is the same. I want to find out 5 minus 4 is equal to 1. So plus minus syntax same. If you want to multiply two things, so suppose I want to multiply 2 times 3. I want to get 2 times 3. I put 2 star 3. Star is multiplication. And then if I want to divide something, 4 divided by 2. So the slash is division. So 4 divided by 2 is 2. So basically you have seen that plus minus multiplication, and division. Everything can be done in a very straightforward manner. Okay, so basically this is nothing but a calculator at this stage, no more than that. And also there is one other function that you need to know is raising something to the power. So I want to find x raised to x to the power y. So 2 to the power 5 I want to find. So I need, which I know that it should be 32. So let's try to find 2 to the power 5. How do I do it? For the 5, I just put this upward cap sign. So that is the one that comes with your 6, numerical key of 6. So 2 to the power 6 is, 2 to the power 5 is this, 32. So this sign is your power sign. So 2 raised to the power of 5. So these are, so basically multiplication, addition, multiplication, addition, subtraction, division, and your finally exponent arithmetic. Everything you can do using Matlab. Now, this is the very basic, but for this you can just use your calculator. Going to the next step, in Matlab you could actually assign values. So for example, let's call a is equal to 1. Okay, and write a semicolon. So a is 1, b is 2. So I write a is equal to 1 and then put a semicolon. There is a reason for that. You may not put the semicolon, that's fine. But the moment you write a is equal to 1 and then press enter, Matlab will remember that a is equal to 1. Similarly, if you write b is equal to 2 and press enter, Matlab will remember that b is equal to 2. So at this point, if I write a plus b, I see 3, right? So I can do these things. Or suppose I want to write b to the power a, which is 2 to the power 1. It should be 2, right? So b to the power a. I see 2. So basically, you could, I transported everything from 1, 2, 3, 4 to AB, that of to the two terms of AB. So that way I can actually write down expressions. So suppose I want to find out b to the power a plus 1 is 4, right? Because that is 2 to the power 2 plus 1 plus 1, which is 2 to the power 2, which is 4. So you could do all these things using Matlab or Octave in this instance, but the same thing. Okay, so this is. Next, what you could do, another power. So this, even till this point, it's not much different from a scientific calculator. But then let's go to the next step. Suppose I want to define a range of numbers. So what I could do is, suppose I want to define all the numbers from 1 to 10. So I want to find out, I want to have a variable which will be called 1 to 10. What this gives me is x is equal to 1, 2, 3, 4. X is not just a number now. X is 1 colon 10, which means I am x is called an array and it has all numbers from 1 to 10. So I did this. Now if I want to find the square of all these numbers, so what I do is x, I put a dot in here and square. So now I have the squares of all the numbers. 1 squared is 1, 2 squared is 4, 3 squared is 9, all the way to 10 squared is equal to 100. So this is how I can do all this arithmetic. Okay, so is everything clear up to this point, or is it too basic? Are you already familiar with all these things? And one question: are you able to see the screen? Because these numbers are rather small.
Sir, so we need to download which software, Matlab or Octave?
As I said, if you have the Matlab access from the institute, then you can download Matlab. Octave doesn't need any of these things. You can just download Octave from wherever you want and start running. Or you could go to the online version of Octave and do the same things over there. So it's all up to you. Both these softwares, all these options will give you exactly the same result. So up to you. Where you can get Octave, get out Matlab. No difference. Okay. Okay, so basically, I hope that the screen is visible to everyone. Let's assume that there is some sound going on. Okay, all right. So I hope everyone is able to see these things. So now if I want to, so what it shows me is I can evaluate all these strings. So now suppose I have already told A is equal to 1, B is equal to 2, C, let's define C is equal to 4. Okay. And now I want AX squared plus BX plus C. AX squared plus B times X squared plus C. See, I can write these things down easily. I have this ax squared plus bx plus c. I can easily write this down and get all the expression, all the values for every value of x. So this is the power. So how does it help us? Suppose I want to plot something. For example, I want to find some value for lots of different different independent variable, lots of different values of x. I could easily do that and plot it. So if I want to plot ax squared plus bx plus c for all values of x between 1 and 100. So what I would do is I will first write down x is equal to 1 to 100. Okay. Now let's call y is equal to ax squared plus bx plus c. Okay. Now if I write plot x comma y, x-axis always comes first, y-axis always comes second. Okay. So plot x comma y, I will see something like this. So this is a plot of ax squared plus bx plus c. So these things you can do easily using Matlab or Octave, so whatever you want to wish. So but ax squared plus bx plus c looks like this when you have x and y. So x-axis is x, y-axis is y. So there are ways to write these things down. So I can write x label. So if I take that x and x label x label is x, I have to do it in quotes, and then y label is ax squared plus bx plus c. So now on the x-axis I am writing x, and the y-axis I am writing ax squared plus bx plus c. So I can name the axis. So now I'm using Octave. So these numbering, these names, they don't look very nice. So if you use Matlab, the curves will look much nicer. So for example, whatever you see here, this x written is very small. So if you use Matlab, these things will look better. So ax squared plus bx plus c, this name of the y-axis, this label, these will be much better. These things will look much better. I'm using Octave so that everyone can know that Octave is good enough. I mean, for our purposes, no difference between Octave and Matlab. But visually, Matlab is a bit more pleasing. Everything will look much more sophisticated. Octave is just a open source free software. So of course, for Matlab you have to pay lakhs of rupees. So it's a very, so of course you'll get some benefits in there. But as a functionally, these two are exactly the same as far as we are concerned. Okay, so this is what we have. So what I have seen, what I've shown here is writing something on the command window. So on the right, I'm writing these things. So this part is called the command window. Here you can write something, press enter, you immediately get the execution. You can do the same thing using the online Octave thing as well. So on online Octave, you go to the right side. So here you write a is equal to 5. You get a is equal to 5. B is equal to 1, you can write b is equal to 1. So you put a plus b, you get a plus b is equal to 6. So x is equal to 1 to 10, you see x is equal to 1 to 10. And also one thing I didn't mention is, if you write 1 colon 10, then you get all 1, 2, 3, 4, 5, 6, all the way to 10. So if you want to get every 2 in steps of 2, so you can write x is equal to 1 colon 2 colon 10. Now you see every second number. So 1, they skip 2. So 1 plus 2, 3, 3 plus 2, 5, 5 plus 2, 7, 7 plus 2, 9. So you could do all these things. So, or maybe you could make it, if you want to make it, every 0.5. So the step size you can change. So the step size is now 0.5. So 1, 1.5, 2, 2.5. So you could do all these, you can play around with all these things. So I really suggest that those who are not familiar, play around these things. It's very fun. It's just You could do a whole lot of things. Just Google it. I mean, if you don't, you can just Google Matlab code for something. If you ask how to do it in Matlab, because Octave, if you Google, you may not get the correct answer. But if you ask for Matlab, everybody has, at least everyone has asked for the same question before. So you can find all the answers on Google. Okay, so this is how you do it. So in Matlab or Octave, you could specify what you want to do, what is the step size, and all these things. So that is it. But whatever we saw here on this side is called the command window. Instead, here you do line by line. So I write A equals 1, then press enter. B equals 1, press enter. And X equals to 1, X equals 1 all the way to 1, 2, 3, 4, 5, 6, all the way to 10, press enter. So I do it step by step and get the result. And then I plotted something. Whatever I do, I have to do it step by step. Instead, what we could do is, we could lump all these things together. So suppose I have so if you go to the left side of this, so you go to the file and you go to new and you go to new script. So in Octave, you go to new script. I'm talking about the software. I'll talk about the same thing for the online version as well. So if you go to up here, file, new script, then you get something like this. On this side, on the left or somewhere, some blank space will pop up. So over there, you can do the same things. Here you don't need to do everything one by one. So you could write A is equal to 1, B is equal to 2, C is equal to 3. Now let's suppose X is equal to 1, 2 in steps of 0.5, 100. So C is 1 to 100 in steps of 0.5. Let me put semicolons in there. And then plot. Then let's call again y is a times x squared b times x plus c. Now I plot x comma y. So I'm plotting y as a function of x. And then I'll have to save it. It'll ask me to save the file. And you see, I have this thing. I have this plot. Very similar to plot to here. So let's call it x label. Name the x's. X label is x. Y label is y. That's plotted. So now my label x's are labeled as well. So x label is x, y label is y. Now the benefit of doing it this way is that I can make small changes, and so I don't have to rewrite everything. I can make small changes. Let's make b equals 3. Then I have some other graph. So it's just like that. So suppose I make b equals c equals 0. Then I should have a linear curve. Sorry, a equals 0. I'm sorry. I make a equals 0. I should have a linear curve. So then bx plus c, straight line. Yes, no curvature. So I can take this thing and keep changing things to see what happens. So that's the fun part. You can just write a script, keep making changes. You can see, and you can make enhancements. For example, this axis. Suppose I want to put some grids in there, just like you have on your graph. So you say grid on. So this graph now has grids. So you can see all these square grids. I don't know if it's visible, but this graph has all these square grids. So you could do all these things using Matlab or Octave. Okay, so the same syntax. You take the same thing, do the same thing on Matlab, you'll get the exact same result, except that the graphs might look a little better. So that is the thing. And sometimes before doing everything, we put a line called CLC, clear all. These things you can skip, no problem. What actually these things do is, CLC means everything is cleared up. So this screen, whatever there on the command window, on the right side of my window, on my right side, everything will be cleared up as soon as I run this program. So if I write this, see, everything is gone on the command window side because of this CLC thing. CLC clears the screen. It cleans it up. Everything is deleted. Then clear all means whatever memory the system might have would be cleared. And close all means if I'm opening some graph before, that graph will be closed. So it's basically you start with a clean slate. That's it. So that's why I have these 3 lines at the top. But after that, my real code starts. So I'm just writing A1, A is equal to 1, B is equal to 2, C is equal to 3, giving some values to X, and then I'm plotting plotting X, plotting Y as a function of X. So that's it. So you could plot any function using this. So if I want to plot a cubic function or a 4th order function, let's say. So I'm putting x to the power ax to the power 4. If I make it ax to the power 6, it's the 6th order polynomial I'm plotting. So it's very easy. I have this written. I could just keep changing things, and then I will get new plots, new values, whatever I wish. Okay. Okay. So any questions till this point? All right. So next, let's do this thing. Let's try to, yeah. Any questions?
Sir, what is this x equal to 1.500? What is this?
So what I'm doing is x, I'm taking all values of x. X I'm defining as an array that has all values from 1 to 100 in steps of 0.5. So if you want to know what x is, you just write here x.
Okay,
So
sir.
what
Okay,
x,
sir.
so x is 1, 1.5, 2, 2.5. So I'm just writing down all values. So because if I want to plot, I have to plot for each value of x, right? So I first look at what is the value of y for x equals to 1, what is the value of y for x equals to 1.5. So this, I do it for every value of x that I defined over here, and then I plotted it, plot x comma y. So I plot the whole thing. Okay, so this is what I meant. Now the next thing is, let's try to use this tool to plot some frequency responses. So how do I do that? So suppose I want to plot this thing. So we discussed this RL filter circuit before. So this was our low pass filter. We said that we claim this is a low pass filter. This is a RL circuit with voltage taken across R, and then there's an L in series with this R. So this series RL filter, and we said this magnitude transfer function is this 1 divided by square root of 1 plus omega L by R whole squared. Now the question is, does this transfer function look like as a function of omega? And we did then asymptotic analysis, said that okay, omega is 0, then you have 1, and then omega is infinity, then you have 0. So that should be a low pass filter. But how do you verify this? And if the transfer function is more complicated than this, you may not be able to actually say that confidently just by looking at the transfer function. The best way to do that is to actually plot it. And we said that typically we plot the dB value of these transfer functions, so 20 log 10 of h of j omega, that is what we normally plot. So let's try doing the same here. Okay, so what we would do is, as I said, these initial CLC, clear all, close all are just customary, nothing to do with. Now let's try to plot this. So let's try to design a circuit. Let's suppose we have some R value. R is 100 ohms. Okay, so R would be 100 ohms. L is, let's call it 10 millihenry. So how do you write 10 millihenry? One way is to 10 to the power minus 3. Okay, millihenry is 10 to the power minus 3. So I'm just writing 10 into 10 to the power minus 3. And this is RL. Now I would like to plot the transfer functions for some values of omega. So I have to define omega. So omega, I will plot from 1 to, let's say, 1 to 50,000. So as omega goes from, that angular frequency goes from 1 radian per second all the way to 50,000 radian per second, I want to plot the transfer function. So next step is to write down the transfer function itself. So what is the transfer function? Transfer function H absolute is 1 divided by something, right? So 1 divided by, down below what I have is a square root, right? Square root of, what is it? 1 plus omega L by R whole square. So 1 plus omega L by R whole squared. This should be it. Okay, so I wrote down h of j omega. Okay. Now I want to plot h of j omega with respect to this. Maybe I will plot the dB value. So h is that. So what is h of j omega in dB? That is 20 log 10. So this is how you write log 10. Log of logarithm to the base 10. So immediately log 10 without any space. Log 10 of h. Okay, so I define h dB and then I'll write it in h dB. Then I'll tell that I want to have grids on. So as I said, grid on. So next, so let's call it example 4. See, I have a plot over here. So this is, let me write the labels. X label is omega. Y label is h. So you have X label is omega, Y label is h dB. So if you plot it, you get something like this. You could actually make the line, width of the line a little larger. So if you think that your line is looking too thin, you could actually make it a little larger, a little thicker. So I made the line width a little larger. So h dB, h. Okay, so we have this. So what do we see here? We see here that h of h dB, the transcaling applied by the filter circuit, becomes smaller and smaller as we go higher and higher up in the frequency domain. So this is exactly the low pass filter that we claimed it was, but we were not able to plot this curve. I just plotted some curve randomly. I had no idea what this curve will exactly look like. But now with Matlab, I can easily plot this. And let's suppose I want to find out what the 3 dB bandwidth is. What is the 3 dB bandwidth of this filter? I want to find out where this value drops down to -3, because these are all dB values. Now that dB value, in order to find where that -3 is, it's somewhere here, right? Because -5 is this, -3 should be somewhere here. But where exactly is it? For that, I can just zoom it. So there is a Z plus in Octave. In Matlab, you'll see a zoom figure, like a it's a zoom figure that you'll easily be able to spot. So you can zoom this part. I'll zoom this part. See? So where is -3 dB? So at -3 dB occurs at 10,000. Omega is equal to 10,000. So that is my 3 dB cutoff. So my 3 dB cutoff is right here. That 3 dB cutoff is at omega is equal to 10,000. Now, if you remember from our discussion, 3 dB cutoff, we also found a analytical expression for the 3 dB cutoff frequency. Did we write this thing? Yes, the 3 dB cutoff frequency is R divided by L. So that is where your HDB becomes -3. So let's verify whether that's correct. So from here, we have seen from this curve that 3 dB cutoff occurs at 10,000. Is that really correct? Let's see. Let's try to find R equal by L. Indeed, your R divided by L is 10,000. So at R divided by L, I have my 3 dB cutoff, which is confirmed by this figure. So I can do these things. Now let's suppose I want to, so the benefit of this is I can just change things. So basically, suppose I have this, then I want to find the behavior if I change the value of in the resistor, let's say. Instead of 100 ohms, I want to reduce it to 50 ohms. What happens? I have something like this. Now, just from the previous figure and this figure, it might be hard for you to tell what exactly is going on. But for that, what you could do is, suppose you want to compare two things. Suppose you want to see what is the filter response for R is equal to 100 ohms and what is the filter response for R equal to 50 ohms. So this is your R equals 100 ohms. So HDB, so let's call it HDB. I can just change the name, right? So this is R100. So this is for R100. So So whenever you give a variable name, make sure that there is no space in between. That's why I'm giving these underscores. So HDB, H underscore DB underscore R100. So I can't keep some space in between. So every variable name should be connected. There shouldn't be any white spaces. And it should always start with some letter, not some number. Okay, so XDB 100. So I do this. So this is the same program as before. I just changed the name to this. Now, let's do the same thing. R equals R is equal to 50. So now what I can do is, so this is R100, R100. Similarly, R is 50, so HDB, HR50. All right, so now what I am able to do is this, R is 50, R is 100. So I can plot two curves at the same time. So I write W omega comma HDB R50. So I'm plotting the transfer function for R is equal to 50. And then after that, I'm writing omega comma HDB R100. So I'm plotting the transfer function for R equal to 100 against omega as well. So I'm plotting these two things. So I'm plotting two curves. So this first part is one curve. The second part is two curves. Okay, so I plot all these things. And let's see whether this is correct or there is some problem. H is undefined. It's saying H is undefined. So I made some line 17, column 23. Yeah. So H. So I changed H. I forgot to change this one. Now you see what's going on. So basically you have two curves, one for R is equal to 50, one for R is equal to 100. Now, how do I know which curve is for which? So for that, there is a technique. I will just put something called a legend. It's called legend. R is equal to, first one was for 50. R is equal to 100. This is called a legend. Now hopefully you can see here. So on top of the graph, now I say R is equal to 50 is the blue graph and the blue curve, and the red curve is R is equal to 100. So suppose you don't want to rely on these colors, you want to change the graph, something in the graph, so you want to change the, put some markers on the curve so that you are able to distinguish it better. For example, if you want to plot everything in black and white, or maybe you are using this figure for some document which some people might print in black and white. So you don't want to rely solely on colors. So what you could do is you could put something in here. So the moment you put it, write something. So I'll put a O in there. What this will do is, in one of the curves, I'll have, this is not a good idea. I will just put this thing. Yeah. So I made one graph dotted, the other graph solid. So now easily you can distinguish that the dotted graph, the red dotted graph is for R is equal to 100. The solid blue graph is the curve for R is equal to 50. But those are just cosmetic changes. But the point over here is that easily using Matlab or Octave, you can figure out what happens to a circuit when you change some parameter value. So you change R from 100 to 50 to 100, immediately the entire curve shifts up, which means this filter that has R is equal to 50 will have a lower cutoff frequency, 3 dB cutoff frequency that will occur at a lower frequency. And also you will have higher suppression, higher attenuation because of this filter, because this is the scaling. So H of dB is nothing but the scaling that the input signals receives. So the higher up you go into frequency domain, higher up you go in the frequency, the more the attenuation that the filter applies to the received input waveform. So basically input signal is suppressed more and more if you decrease the value of R. So for any given frequency, suppose you fix the frequency at 30,000. I just arbitrarily chose 30,000. So 30,000, you take the same filter, but you keep changing its resistance. So same input, same circuit in terms of inductance and everything else, except that you keep changing the resistance. You keep making the resistance smaller and smaller. In that case, you would see that the smaller the resistance, the more the suppression of the input signal, the less output you get for the same frequency. The frequency is constant. So all these things you can see from such curves. So it's very easy to plot these curves and visualize. And again, if you take just this part for the 3 dB frequency, so you could look at this and see that the 3 dB frequency for R equals 50 would occur at a much lower value, somewhere here, whereas for the higher frequency, for R is equal to 100, it will occur here. So actually we know for sure, this is the 5000. So at 5000 radian per second, you will get the 3 dB cutoff for the RL filter with R is equal to 50. So that comes from a theory, and it is also corroborated by this experiment. Okay, so this is how you can use Matlab or Octave to plot these things. Then okay, so that's one thing. And then one thing I would like to show you is, so this is another for low pass. Let's go here. Okay, so if you remember, I wrote this down just before this tutorial to show you, because I didn't want to go through write this whole thing again during the class time. It just wastes a lot of time. But if you remember, we did some band pass filters. So we had this band pass filter, and we said that the band pass filter response, so the filter would look like this, with a sinusoidal input, and then you had this output taken across the resistor, and then the rest of the filter consisted of one L and one C. And we said that the output frequency, the scaling due to the filter, or the h of j omega, look like this. So that h of j omega, we said, I made this point that it's very hard to do this asymptotic analysis just by looking at this, because it's how do you say what happens when omega goes to 0? Because when omega goes to 0, it's easy to make this omega L by R 0, but then the other term becomes infinity. So one term becomes 0, one term becomes infinity. It's easy. I mean, it's not that hard, but it's slightly more complicated than the high pass filter or the low pass filter. So it's instructive to actually take this function and plot it out and see what happens. So if I plot this, so what I'm doing is I'm just plotting the same thing. So h dB is h of R square root 1 omega L by R minus 1 by omega RC, the whole thing squared, and then I'm taking it, taking the ratio. So that's h of dB, h, and then h dB is 20 log 10 of h. So if I go ahead and plot this, I get this figure. So let's zoom it up. So I get something like this. So this is my curve. So when I plot it from all the way up to 2500 omega. So I get something like this. It goes up and then it comes down. So it's definitely a band pass filter. So even from here, you know that it's going up and it's coming down. So it doesn't look as exactly like the ones we typically draw. So those are just some arbitrary waveforms that we drew in our classes. But in reality, what happens is something you can investigate using Matlab. Okay, so this is the thing. So again, you can do the similar things. So suppose I decrease L, what will happen? It looks very different. So basically the bandwidth became very large. I have to go farther up in the frequency domain. I increase L, what will happen? It will become sharper. So I made L equals 100 millihenries. Now my input became much sharper. My transfer function became much sharper. So all these things you can play around. You take the basic code, you keep changing component values, and you will see different types of outputs. You can play around with the output. You can see, you can plot one output on top of the other. So just like before, you could take this, plot it for different values of R, or maybe plot it for different values of L. So keep changing these values and you will see the variation, the pattern in the variation, how these things change. I guess this is the basic main strength of simulation tools like Matlab and Octave. So you could easily write down these equations. You can plot different curves. You can play around with component values or input values, and you can compare what happens when you change certain things. So all these things are possible using these simulation tools. These are also called scripting tools. Some people call it simulation tools. Some people call them programming tools. But whatever they are basically very powerful pieces of software. So this was a basic introduction to Matlab along with how we might use them for our purposes. So any questions on this introduction? Okay, so one last thing. Suppose I have this, but I don't have Octave, and I want to do it online. How do I do it? If I want to do that, sorry. So if I want to plot this thing on Octave Online, what I might do is I'll go to Octave Online. I signed in already. So what I would do is I'll go here. On the left corner, I'll see this create empty file option. So there's a plus sign in here. So I click on the plus sign, and then it will suggest some name. So please enter a file name. It's called myscript.m. Okay, I put it myscript.m. Okay. Now it has some basic thing like display hello world. I'll remove that, and I'll like to see. So plotting, I don't know whether you'll be able to plot these things over here, but you can definitely get the values. So let's see whether you are able to plot the values. I haven't tried this in a long time. Okay, I think I got disconnected. We'll probably have to start from the scratch. Let's go to Chrome because Firefox might have some issues. I mean, you'll all be able to download Octave, so online is just for the rare case where you are not able to do that, but still. Integrate, okay. Let's call it myscript1 to be sure. I go here. So unfortunately, you are not able to plot these things, but what you could do is you could write down the values of each of the W, and then take these values to, let's suppose, okay, so basically you could see what is the value. It actually plotted as well. So what you need to do is you create a script, clicking on this plus sign on the top left. That will create some empty file. On the left, you will be able to see the name of your file. You go to that file, you write your code the way you want to write it. Then you go here, you put a save file on top, save file, and then click on run. Okay, and then that will run your code. And then you see this thing. So you see the same thing. But I would suggest to try getting the real Octave or real Matlab. That's much better. But if you don't have that for some reason, maybe because of data, you don't have enough cellular data to download these things. So in such situations, you could also use online Octave. And online Matlab might also be there, but again, to access online Matlab, just check with IIT Bhubaneswar whether you are able to log in there. If you have some difficulty, let me know. I'll ask around and let you know. But this is how you use these tools. Okay, so hopefully this made some sense, and I hope that you found these things interesting. So what I would do is I would give you these codes so that you can play around with that. And next week we will have some exercises, homework exercises, where you will be plotting some codes, plotting some transfer functions. So any questions that you have for me? No, so fine then. So what we will do is we will stop here today. I will send you these codes and you try them out. If you can't get hold of Matlab or Octave, then you could go online and try it out. And just any questions? I think somebody. Okay, so then maybe there's just some random noise. Anyway, so basically, as I said, you try them out. I'm going to send you these codes. You see, you have to Google things around a little bit because you are, if you're doing it for the first time, you'll not be able, you may not be able to figure out certain things on your own. No problem. We are doing the most basic sort of programming in this class, so that will be. I think it will be rather interesting for you. So let's stop here then. It seems there is no question. So we will